It's actually kind of hard for me to assign homework problems from the material that we're covering. I know I gave you 2 problems from the last bit, but from this week's stuff, it's kind of hard to give you homework problems. So I'll pull some out when I can, where I can, but it's not guaranteed. Okay. So the weak source. The weak source. All right. So, it's funny, I felt really exhausted today, and I'm like, oh, it's because I'm going to teach about the weak force when I'm weak. Weak as an ass. But anyway, I call this lecture the weak sauce, and I really don't know why, but it's just a good word, sauce. Anyway, it was probably like buried like 6 years ago when I taught this course. It was part of a really funny joke that I've forgotten. So anyway, we'll just go without it. Anyway, so we've known a lot about E&M for the last 100 years or more now. I guess when I taught this course it was 100 years, now it's even more. But we might ask, what makes QCD and the weak interactions harder? Why did we only learn about the QCD and the weak interactions within the last 40 or 50 years? Well, for QCD, why is that the case? What makes QCD harder than QED?
It requires higher energies to investigate?
Well, it does, but I mean, of our work in calculating things with QCD, what makes them harder? Go for it, Sergio. It's a non-abelian group, so you get interactions of the gluons with each other, but also, you have 3 charges, and so you've got all of these weird transformation matrices. It's a lot of matrix notation that we didn't have in the QED. I mean, in the QED we have spinors, so we have to work with those, and of course we have space-time vectors. But in QCD we have to introduce color space, which is this 3-dimensional space, and you get the color basis vectors, and then you get these matrices which act in the color space, et cetera, et cetera. So QCD is just kind of a headache. But more importantly, I think what makes QCD so challenging is that the particles that it is exerted on, which is quarks, do not live freely, right? Quarks can't be seen. Neither can, in fact, gluons, the force-mediating particles. They can't be seen individually because of this whole idea of color, what is it? The hidden color hypothesis? I can't remember what I called it, but anyway. Okay, so the weak interactions are similar. First of all, remember when we talked about the weak interactions, did I turn this on? Yeah, I did, sorry, thank you. When we talked about the weak interactions in the Lagrangian formalism, we had this spontaneously broken symmetry, okay? And that, of course, makes things a bit ugly. But the weak interactions are important because the weak interactions can do the one thing that no other force can do, and that is what? Hi, Ross. Thanks for waving at me. What can the weak interactions do that no other force can do? Exactly. It actually mediates decay, where you have one type of particle to begin with, and then you get different types of particles coming out. Okay, the other interactions can't do that because they don't change the particle flavor. The word flavor just means the type of particle we're dealing with. Now, first and foremost, it's kind of weird that these are called the weak interactions, because if we look at the couplings between the various interactions, what we find actually is that the strong coupling is the strongest, the electromagnetic coupling is the weakest, and the weak coupling just kind of sits in between, okay? So calling these interactions weak, it's kind of inappropriate. However, if we just sit and ask what's the probability of various things happening, it turns out that the probabilities associated with the weak interactions are rather small. Okay, now we talked about last time why the strong interactions appear to be weaker than the electromagnetic, and that's because of this colorless hypothesis or whatever. But why are the weak interactions, why are they less prevalent than the electromagnetic interactions? Any guesses? Hi, Ross. Any guesses? Anybody remember what important ingredient of the weak interactions is? photons and gluons are massless, but the force particles associated with the weak interactions, the W plus minus boson and the Z boson, they are actually massive. In fact, they are really massive. And it turns out that even though the coupling of the weak interactions is sort of in between, the fact that the force is mediated by a very, very massive particle takes the probabilities that come out of Fermi's golden rule and drives them super low. So the probabilities are low even though the coupling is not that low. Okay? All right, so today we're going to talk about some formalism, and then next time likely we'll get into direct calculations, because one of the important things about using the weak interactions in calculations is you can calculate the lifetime of things because they're decaying. Okay, so that's an important calculation. All right, so let us turn to an important element of the story. So first and foremost, W plus minus change lepton flavor within a single generation. Now I know there's a lot of words in there that I've used, but you're probably not that comfortable with, so I'll go in and define them. So first of all, remember that for the weak interactions, we take our leptons. These are the matter particles composed of electron, muon, tauon, or tauon, muon, I say electron, neutrino, muon, neutrino, and tauon, neutrino. So I'll just write these up really quickly. Okay, and then each of these categories is called a generation. So this is first generation, second generation, third generation. And we think of them in terms of generation because basically everything to the left is lighter than anything to the right. Kind of. I mean, these neutrinos are in principle, at least at the level of this class, massless. So the neutrino here is definitely less massive than the electron, but the electron is lighter than the muon, which is lighter than the tauon. Okay? But anyway, these different brackets are called generation. This is the collection of leptons, and that's of course different from the collection of quarks. The quarks will also put in generations, but we're going to have to talk about that in just a minute. Okay? Now, of course, what the W plus and minus parts of the weak interaction do is they change you from either this to this or from this to this, and that can be done by the diagram, the fundamental diagram that looks something like this, where we might have an electron come in, an electron neutrino come out, and then we'll have the weak boson moving away from the vertex like that. Or we could reverse the direction of everything if you want. Have a W plus coming in and an E coming out, and a new E coming in. Okay? Notice it's the W plus and minus bosons which actually change which lepton we're working with because they change the charge. The Xenon boson, which we'll talk about later, it is chargeless like a photon, so it cannot change you from this to this. Okay? Now, in a simple world, this story of how W plus and minus affects leptons would carry over to the quarks. Well, this is the weak interactions. They are a hairy headache. I don't know why they're hairy, but they're a headache, okay? It turns out pretty much every element of the weak interaction story is just a little bit more complicated than it needs to be, okay? So first of all, let's take our quarks and let's arrange them really quickly. So we might say, all right, for quarks, we have the following. We have up, down, charmed, strange, top, bottom, okay? And writing of the quarks in this fashion is relevant because if you think about the electromagnetic interaction of the quarks, everything that's a top element has electric charge 2/3, okay? Whereas everything along the bottom has electric charge minus 1/3. If If you ever get confused about that, just remember that a proton is an up, up, down. Proton has charge plus 1. Okay? And a neutron is up, down, down. Okay, that's kind of the way it plays out. All right? Unfortunately, the organization of this in terms of mass doesn't work out. It turns out if we want to do it in terms of mass, we should write up, down, and then strange charmed, and then bottom and top, which is, of course, weird crap. But now we have increasing mass and increasing mass. So heavier than that, heavier than that, heavier than that, da 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 da. Okay? All right. Now, I'm going to give you a little bit of a history lesson. Now is the time I feel like it's good to give you a little bit of a history lesson. The book gave the first chapter, the history of particle physics, which I think was the hardest thing to understand. It's way easier to understand the history of physics after you kind of understand the physics. Okay? So now I'm going to dig back into history a little bit and tell you some more things because there's sort of an important advantage of theory that I'm going to get to. So first of all, in 1963, and this is around when we're going to talk about things, in 1963 there were only 3 known quarks. There were the up, down, and the strange quark. Okay? Notice those are the 3 lightest quarks. All right? These quarks had not been observed directly because you can't get a quark by itself, but they had been inferred from the calculations that had been done and the experiments that had been done. And so they knew that protons and neutrons and so forth were made of like these 3 little objects, and the only versions they could come up with were up, down, and strange. And then, well, it turned out these 3 weren't giving us full understanding of every single experimental result. There were a few experimental results which weren't really agreeing with this. So Cabibbo, he realized that both the D and the S should be related via the following diagrams. Okay? Now, this is what we would expect if we're starting off with a down quark, which has a negative 1/3 charge, and we send out a minus charge, then we're going to be left with a positive charge of 2/3. Okay, the difference in charge is just 1. Okay. Moreover, this is only taking the down quark and turning it into an up quark. It's remaining within the generation, which is exactly what we find when we talk about leptons. The W's change electrons to electron neutrinos, mu1 to mu1 neutrinos, tau to tau neutrinos. Okay? But what Cabibbo suggested is that in addition to this vertex, if we include this vertex, then we might actually get better agreement with experimental results, and it turned out that was the case. Okay? Now, let me go ahead and write down what vertex factors are playing a role in this story. So minus IGW over 2√2 gamma mu, whoops, 1 minus gamma 5. We'll talk a little bit more about the structure of these in a bit. And then I've got this cosine of theta c factor in that one. And then in this one, it's minus IGW over 2√2 gamma mu 1 minus gamma 5 times sine of theta c. Okay? Where theta c is often called the Cabibbo angle. Theta c. See? Good. All right, awesome. Turns out that the Cabibbo angle, if you are not measuring it, is about 13.5 degrees. Okay? So these clearly win in terms of the competition between these processes, because, you know, cosine of the smaller angle is a bigger value than the sine. Okay? Well, that's interesting, but look at what we're doing. This is taking down to up, remaining in a generation, but this is taking strange and giving you up. This interaction is actually not satisfying that it should stay in the generation. Okay? So this is the opening to an interesting change in how the story plays out. Because here it's super clean. You just change E to new E, you know, it's always clean. Here, though, we've got the possibility that the interactions could change. Now, this is back when UDS was the only part of the story. Okay? Now, well, it turns out that while adding in this calculation actually made many of the experimental results agree with calculations, there were some that didn't, and here's an example. Suppose we have a K0, okay, which is a neutral cation, and a K0 is actually an anti-strange quark combined with a down quark. Okay? And we might be interested in the process of K0 decaying into a mu plus mu, or mu plus, that's why I wrote it this way. I can't say that. Mu plus plus mu minus. It's weird. Anyway, this giving you a muon and an anti-muon. Okay? K0 is electrically neutral, doesn't have a charge. This has a plus charge, this has a minus charge. Okay? So it turns out that K0 can decay into a mu and a mu plus. And to do so, it does it via this prescription. Where in the intermittent part, it gives me a U. And then over here, I get a mu neutrino, and a mu. Okay? Now, what role is the Cabibbo angle going to play in the expression for M there, for that diagram? How do you think it's going to appear? Sam?
I actually have a question.
Oh, yes.
So the cation is a combination of a down quark and an anti-strange quark?
Yes. Okay. Notice the down and the strange have the same minus 1/3 charge, so if you're working with a down quark and an anti-strange quark, the anti-strange quark has plus 1/3, so it's neutral. The combination is neutral. Okay. Don't pay attention to this, because this is where I need to organize it for the charges. So look, when we're doing the calculation of M, for every vertex, we write down a vertex factor. So we've got two vertices in here. One is like this, and one is like this. Right? We've got down turning into U, and then U turning into S. So we're going to get this factor times this factor, so the term that's going to enter is basically cosine theta times sine theta. Okay? Do we get those factors in these vertices? No, because those are leptons. Leptons don't do this mixing stuff. Okay? However, if you calculated the decay rate of a cation based on this leading order contribution, you get a value which is much higher than the actual value. It turns out that kaons live a lot longer than this calculation predicts. Okay? So this was an interesting puzzle, which was addressed in 1970. Another wonderful year. And in 1970, Glashow, Iliopoulos, and Mayani, also known as GIM, this is called the GIM mechanism, proposed a canceling diagram where they said, okay, fine, we're going to have this process that's part of the decay of K naught, but we're also going to have this one, where they're going to say, all right, fine, we're going to have S down strange mu neutrino mu, and in here we're going to put a new quark. Okay? Where this quark will be such that this diagram is going to be governed by minus cosine theta c sine theta c. Because if you have this new quark, the leading contribution to m, the amplitude, is going to be this plus this. Well, cosine theta sine theta minus cosine, those are almost going to cancel. They're not quite going to cancel. Okay? All right? And this is basically because the vertex factors in this diagram will be this and this with one of these minus. Okay? Don't worry about that. Well, they called this thing the charm quark. This was theoretically predicted as a resolution to the fact that this calculation wasn't giving them the right answer. They discovered if they introduced another quark to the theory, it fixed that. The lifetime of K came out more like they were observing. That was in 1970. Guess what happened in 1974? I was born. And they found it. But more importantly, no, so in all honesty, in 74 it was found. Okay? So it turns out that the way that we can do this story is kind of interesting. We can define d prime as d, and I guess I should go ahead and say this really quickly. You're going to need these diagrams, so let me just say, if I have d in and charmed out, then this is proportional to minus sine theta c. Okay? It's got all the I, G, W over 2 root 2 Gim me 1 minus mu 5. If you have D coming in, or sorry, if you have S coming in and C coming out, then it's going to be proportional to cosine theta C. Okay, hence the combination will be proportional to minus cosine theta, sine theta. Okay? Now, given that, it turns out that we can write d prime as a linear combination of the original d and s in the form of d cosine theta c plus s sine theta c. And then we can write s prime as minus d sine theta c plus s cosine theta c. Okay? Then, what we find is that the W plus minus rotates doublets, but the doublets involve up and down prime and charmed and stranged prime. So if instead of up, down, and charmed strange, which I already know it involves the mixing of generations, if I instead think of the generations as up and down prime, where down prime is defined as this, and charmed and strange prime, where strange prime is defined as this, then it turns out that the W plus and minus rotate me within a generation without moving across. Okay? So we've re-achieved that sort of ideal within a generation kind of activity, but we've had to take these linear combinations of down and strange to do that. Well, let me ask you a question. These are superposition states. Like D prime is not a pure state. It's a superposition of DNS, and S prime is not a pure state. It's a superposition of DNS. When have you encountered superposition states? Anyone? When have you encountered them? In what class? Quantum! Yes, quantum. Thank you. What gives rise to superposition states? Hey, Russ. In quantum mechanics, if you're playing around in quantum, how can you create a superposition state? Sam?
You don't look at it?
Well, no, we want to create a superposition state. I mean, not looking at as kind of, that'll leave it a superposition state if it is a superposition state, but how can you take a state or anything and just force it to be in a superposition of something?
Introduce uncertainty somehow.
And how would you do that?
The example I can think of is put something with polarizations through a birefringent crystal and have them overlap.
That's way more complicated than it needs to be. I mean, yeah, that'll work, but it's way more complicated than it needs to be. So, say it again.
Rotate around a few axes.
Well, actually, that's an equally useful thing. So just remember that if I measure the position of something, and I know its position, then it's in a superposition state, right?
Yeah.
What is it in a superposition of? Momenta. A definite position state is a superposition of momenta. Likewise, a definite momentum state is a superposition of space, location. Why can't we know definitely both momentum and position?
Heisenberg uncertainty.
Say it again?
Heisenberg uncertainty.
Right, but how in terms of the operators can I discern that? They don't commute, right. So if I have two operators corresponding to observables and they don't commute, if I measure one of them through some process, I am guaranteed to be in a superposition of the other. Okay? Does this make sense? So, well, that's interesting. Oh, wait, hold on. Now, we've got something which is in a superposition state here, and that might lead you to wonder, why is this in a superposition state? Well, it turns out that there are two operators in this story. One of them is the Dirac Hamiltonian, which we might just call H hat B. And then there is the weak vertex operators, which I'll just call V hat W. And it turns out that these don't commute. Okay? Now, I'll go ahead and give you the resolution to this story. I have it written up in my notes later on, but I think I can go ahead and throw it to you. First and foremost, like, if you have the particles just traveling along, then they're going to be essentially in eigenstates of the Dirac Hamiltonian. But when a particle, which is a combination of them, decays, it's going to decay by the action of this operator. And that's in a sense like measuring this operator. But the measurement of this operator means you're going to be in a superposition of these states. But a more complete way to think about it is as follows. The state of quarks is created through the strong interactions. And the strong interactions identify these generations. Okay? However, the decay of particles occurs through these generations. because the strong interaction creation operators, the ones that are relevant for the strong interactions, don't commute with the decay operators. Okay? So I'm just trying to get some motivation for why these linear combinations come into the story. Turns out you are created by one process, but you decay via another process where those two processes involve matrices which don't commute. So if you're in an eigenstate of one, you're going to be in a superposition of the eigenstates of the other. You follow? We're not going to trace through the details of that. Rather, we're going to jet ahead, because it turns out that right now we've only got 4 quarks. We know there are more. Yes?
Sorry, what's the name of these quarks with prime and the other one? They have different names, or?
No, this is just a linear combination of the D. So these primes are just, they're basically the eigenstates of the weak interaction operators. They just call them D prime. And yeah, we don't have another name for them besides down prime and strange prime. I don't have another name for them. Maybe it exists.
That just makes sense in that weak interaction.
Yeah.
Because I know that all the time when one reads about particle quarks, I think that they refer to the others without a prime, right?
Well, right, because it depends whether you're doing a weak interaction or if you're doing a strong interaction or a QED interaction, you'll just use these labels. It's only with the weak interaction that you need to use these labels. But actually, you don't need to use these labels. You can use the up-down charm strange. You just have to realize that the interactions can change the generation. So that's another way of thinking about it.
And in the experiments, what do we detect? Quarks with prime?
Well, if you're measuring, so you're not detecting any quarks because quarks can't be isolated.
Oh, yeah.
Rather, you're calculating the decay rate. So you're maybe looking at the lifetime of a kaon, okay? So when you're doing the lifetime of a kaon, you've got to include this diagram and this diagram, and you also get these mixing factors, the sine theta and the cosine theta. I mean, obviously, if you just had cosine theta is 1 and sine theta is 0, these are not mixing. But the fact that sine theta and cosine theta are neither or 0 nor 1 is what gives rise to the mixing. And this contribution and this contribution have to come in with these same factors. So let me actually extend the story to where it ends up, because it plays along with this. It just makes it a little bit more complicated. And that is, after GIM proposed the charm quark in 1970, and before I was born, in 1974, when they found the charm quark, turns out Kobayashi and Maskawa said, why stop at 4? Why don't we introduce 2 more quarks to the story? Well, once again, this was a theoretical prediction well before even the charm quark was discovered, but they had their reasons. So what Kobayashi and Maskawa realized was, if you introduce 2 more quarks, then you can create these primed states of these quarks, the down, strange, and bottom, okay, where we're going to go here to top and bottom prime. And you can get these from a linear combination of the down, strange, and bottom via the following matrix. And I'll just really quickly write this down. Where this acts on down, strange, and bottom. Okay? Notice if you just focus on down and strange and you just use the upper left and the first 2 here, you reproduce this set. Okay? Where this is going to be cosine theta, sine theta, minus sine theta, cosine theta. Obviously, though, this is acting on a 3-component thing, so we're going to use a 3x3 matrix. Now, what's important is that this thing is approximately the diagonal. So the largest terms by a long shot are the diagonal ones. Those are the terms which, if those were the only terms, and this was truly the diagonal, it would just take U into D, C into S, and T into B, and it wouldn't mix them. The mixing comes from the off-diagonal terms. Okay? Why would they do this? Why would they propose this? Well, it turns out the insight that they had was, if I have a 3x3 matrix, which is mixing the quarks, as opposed to a 2x2 matrix, which is what I would use to describe this, if I have a 3x3 matrix and that matrix is complex, there's no way that I can redefine things to get rid of the complexity of this matrix. It turns out in 2 dimensions, if I have a complex matrix, I can redefine my bases so that this thing becomes a real matrix. But in a 3x3 case, you can't do it. So this is a complex 3x3 matrix. It has to be, okay? Now what's important about that? Well, it turns out that the presence of a complex matrix mixing the quarks is what gives rise to a very important process called CP violation. Okay? CP violation in the weak interactions was actually something which was detected in 1964. So well before this story was playing out, it was realized that the weak interactions are violating CP. We'll talk about CP in due time, okay? But what Kobayashi and Maskawa realized was that if they took Kabibo's story and extended it to 2 more quarks with a 3x3 mixing matrix, the fact that it's a complex matrix would give rise successfully to CP violation. So there you have it, the prediction of not 1, not 2, but 3 quarks before they were ever detected. Okay? Does anybody know when we found the last quark?
1995.
1995. Okay. So the final top quark was found quite late in the game. Now, okay, yeah, okay, so, you know, this kind of like, it's a little bit messy when you do calculations. Obviously, when you do calculations in this case, you're going to get all these funky terms, and they're just going to, you know, change the vertex factors in the calculation of n by a bit, so it's not that big of a deal. Well, we'll see. So let's first and foremost, before we carry on with this, let's go back to Z0 for a moment, because we haven't really touched on Z0. Z0 plays an interesting role. So let me get rid of this, and let's talk about Z0.
Do we know that there aren't like 2 more quarks that we just haven't discovered yet?
Well, that's an interesting question. First of all, the idea that there are 3 generations of quarks as well as 3 generations of leptons, we don't have an explanation for in the standard model. However, starting at a more fundamental level, like maybe string theory, then string theory would have things unified, you know, in a more cohesive way, but then in the breaking of string theory through compactification of the extra dimensions or whatever, that might actually explain why particles are broken up into 3 generations. So what I'm getting at is if you were going to propose the existence of more quarks, you're likely need to propose the existence of more leptons as well. But proposing the existence of more leptons is problematic because you're also going to bring in yet a new neutrino, and the neutrinos are light. So it seems like we would have already detected a new neutrino if there was a 4th generation of leptons, right? So it could be that there are more quarks than there are leptons. That's possible. It doesn't really seem like it would come from a more fundamental prescription. I mean, this is the standard model. This isn't a theory in a sense. But, yeah.
Why did we find the lighter quarks and leptons?
Why do we find the lighter ones first? Oh, well, what you can create in any process is just based on how much energy you have at your accelerator. So, you know, if you don't have enough energy in your accelerator to reach the rest mass energy of a W+, you can't create a W+. It's impossible. You'll have virtual W+'s in the process, but as far as having a W+ that comes out that you can actually detect, it lives long enough to detect, so it's real, the W+ has to have the mass of a W+. The W+ mass is really large. If your accelerator is not accelerating things with enough energy to create a W+, then you can't see it. So basically, you know, we're just building up what we see by the energy scale that we're colliding things with. Yeah. I mean, this is the short-lived stuff. Long-lived stuff like protons. Protons are heavy, but they're long-lived, so you don't have to create them. They're just out there. All of the other particles, aside from neutrons, protons, and electrons, all of the other particles will decay. So you have to create them. They're not just gonna, they're usually not gonna just exist. You have to create them by smashing things together and smashing things together with enough energy to give you those particles with their rest energies. Does that make sense? Okay. All right, so now let's turn to the Xenon for a bit. Now the Xenon was theorized in 1958. Okay, so this is a pretty old one, by someone named Bloodman. But it wasn't until 1961 that Glashow came along and gave it a real interesting interpretation in terms of the unification of the electroweak theory. Okay, so Glashow in 1961 is really the person who said, you know, the electromagnetic and the weak interactions, I think we should actually unify them. And so he kind of came up with this idea of SU2 left cross U1 hypercharge, and then you break it down to U1 electromagnetism. Yeah, I'll skip that. Okay, so, well, yeah, no, I'll say this. So this was theorized in 1958, fleshed out in 1961 by Goldberg, or by Glashow, and then given firm footing in 1967 by Weinberg and Salam. Okay. And the Weinberg and Salam contribution were basically, they were integrating the Higgs mechanism into the decay and the mass generation and all that stuff. So they kind of finalized the story. However, Xenon was discovered in experiment in 1973. Okay? So you might wonder if something has already been predicted and its sort of details have been fleshed out, why did it take so long to get the Xenon? Okay? Well, remember that the Z0 has this interesting property. That if I have an electron coming in, an electron going out, an electron going in, electron going out, this can of course be mediated by the photon. Okay? But it can also be mediated by the Z0 boson. Okay? That is, any diagram where you have the exchange of a photon, you can replace the photon by the Z0 boson. They're both electrically neutral. Okay? Of course, the vertex factors are going to be different. But nonetheless, you're going to, if you get a contribution like this, you're also going to get a contribution like this. However, the mass scale of QED is much greater, much less than the mass scale of the weak. Okay. So it turns out that if you have an exchange of a massless particle, that leads to a much higher probability contribution in the exchange of a massive particle. And we'll see that when we write down the propagators in the Feynman rules for this. Okay? So, given that, well, actually that's, okay. I need to interpret what I'm writing. This is not mass. This is the value of m, the exchange, the transition function. So this is the thing which enters into our calculations of the Fermi-Gould rule like that. So in that case, that's much bigger. But this is much bigger than this because the mass scale of the weak is much larger than the mass scale of QED. Okay, so these are not masses, these are these transition amplitudes. Okay, that's why I had it written like that in my notes. Anyway, okay. So given that this is always going to dominate, how are you ever going to confirm that this is actually happening? Well, let me ask you. Does there exist a process with the exchange of Z naught where the Z naught cannot be replaced by the photon gamma? Huh? Say it again? Exactly. If we have an electron coming in and an electron going out, but we have neutrinos, well, this diagram is mediated by Z naught because this is the weak interactions and Z naught will provide the vertices here. However, the neutrinos are electromagnetically chargeless. They will not undergo the simple exchange of a photon. Okay? This process was observed in 1973. Obviously, it was observed later because it involves neutrinos, and neutrinos are just terrifically difficult to detect. Okay? Now, you might argue, wait a minute, no, that's not what they measured, because what they measured was actually this. Mu1 neutrino, electron W, muon neutrino, electron neutrino, and electron. Okay? The ins and outs are the same in these two diagrams. But this diagram is built with W's instead of Z naughts. How do they know they saw this versus this? How do they know this is more important than this?
Number of vertices.
Yeah, the number of vertices. This has only got 2, this has got 4. Okay. All right. So let's talk a little bit about using the Z naught. And of course, this is going to come with its own headache. So to use the Z naught, Z naught, first and foremost, it doesn't change flavor. Okay, it can't take you from an up to a down quark, or from an electron neutrino to an electron, because in order to mediate these processes going from the top to the bottom, you have to change the charge. Because the charge of this is different than the charge of this, the charge of this is different than the charge of this. So to mediate the interactions which change these, it has to carry away or bring in charge. This is neutral. It can't do that. Okay? So we have that the Z naught boson is not going to change the flavor. The flavor is just the name of the particle. So it acts a lot like gamma. In fact, there's no Ckm nonsense. because the Ckm matrix, the Kabiba-Kobayashi-Moskawa matrix, comes in as part of this flavor changing process, okay, where you got to change from the unprimed to the primed, okay? You're not changing the flavor, so the Ckm matrix does not play a role here. So Xenon's looking pretty clean, right? It's actually, it's kind of just behaving like gamma. No. Nothing in the weak interactions is clean. It's all filthy, okay? So, well, recall that the vertex factor is, for the examples I've given you, minus I GW 2 root 2, and then it's gamma mu 1 minus gamma 5, okay? And for quarks or leptons with the plus and minus W bosons, you're going to have to introduce the Ckm matrix quantities. So since we don't have to deal with the Ckm matrix quantities, maybe that is the vertex for the Z interaction. Turns out it's not. Turns out for the Z vertex, what we need is the following. We can take this and say CVF minus CAF gamma 5, where we have F can be any of the generations, or sorry, any of the flavors. So we can take it to be the electron neutrino, the muon neutrino, or the tauon neutrino, or we can take it to be the electron, the muon, and the tauon, or we can take it to be the up charmed top quarks, or we can take it to be the down strange and bottom quarks. So those are my 4 different families, if you will. And then depending on which family you're in, that's the F, that's the labeling, which family you're in is the superscript. You have CV is 1/2 minus 0.0806, 0.2204, and minus 0.3602. Those are pretty nice numbers. And then, to really make it a headache, we have the factors of CA. These are the coefficients in front of gamma 5. In this case, this is going to be a royal pain in the ass. This is going to be 1/2, minus 1/2, 1/2, minus 1/2.
That's awful.
I know, it's terrible. Doesn't match up with the CVs at all. Okay. Well, turns out the CV vectors are not as bad as they look, because obviously 1/2 is equal to what? 1/2. Just kidding. It's equal to 1/2. However, minus 0.0806 is minus 1/2 plus twice the sine squared of an angle, whereas 0.2204 is 1/2 minus 4/3 the sine squared of the same angle. And last but not least, minus 0.3602 is minus 1/2 plus 2/3 sine squared theta W. Okay? Now you might say, what the hell's happening? Well, it turns out that theta W is the Weinberg angle. And it takes the value 28.75. Okay. So yeah, we have this really weird angle that's determining these coefficients in terms of the one here. The CA coefficients, those are pretty simple, but this theta W angle, it's like, yeah, it lets you calculate those in a kind of simple way, but what the hell is it? Well, turns out, if you want to know the coupling associated with the weak bosons, what you do is you take the coupling of the electromagnetic interaction and you divide it by sine of theta W. then, if you want to know the coupling of the Z boson, you take the coupling of the electromagnetic interaction and you divide it by sine of theta W cosine theta W. Moreover, if you want to know how the mass of the charged bosons is related to the mass of the neutral boson, it's just MW is MZ times cosine theta W. Now I will ask you, what process do you think theta W is born from? Not yawning. What process? Look at what it's bringing into account. That's electromagnetism. This is a weak interaction. That's electromagnetism. This is a weak interaction. These are the mass factors. Does anybody remember that story where we said that electromagnetism in the earlier universe was unified with the weak interactions? They were a single interaction. And then, due to the Higgs mechanism, it was spontaneously broken into electromagnetism and the massive weak interactions. Well, in that process, this quantity theta W played a role, and that's why it's linking up all of this information. And that's why it's playing a role here as well. Okay? So, of course, if we worked with the theory in terms of its non-broken form, if we wanted to do calculations using SU2 left cross U1 hypercharge, the story would play out much cleaner. Okay, but we use the spontaneously broken form of the theory to do calculations at room temperature. All right? Now, I'm going to finish up with just a brief conversation about this gamma mu 1 minus gamma 5 factor, which is obviously playing a role in all these weak interaction vertices. And this will give us a short hint into what we're talking about by these violations, and then we're going to get the hell out of here and come back Thursday for some fun. I feel like this is like your preparatory, boring-ass lecture, just to get you pumped up for what we're going to do on Thursday. Although I still don't know what the hell I'm going to talk about on Thursday, but I've got plenty to throw on you. I mean, I could actually keep you in here through the comedian and into fireworks, probably, talking about string theory. But anyway, it's fine. Okay, so let's talk about this factor, gamma mu 1 minus gamma 5 for a minute. Okay, this obviously is present in all the weak interactions in some form. Even here, you know, you got gamma mu times something minus something times gamma 5. So what is this thing doing? Well, remember what parity is, okay? Parity is a reflection of an odd number of coordinates. Okay? When did I talk about parity? Anybody remember? Say it again?
Wasn't that we're talking about spins or the special groups?
Yeah, so if you take O3 and you reduce it to SO3, you're removing from this set the parity transformations. Because SO3, they're all continuously connected to the identity. That makes them a Lie group. But if you include with the continuously connected transformations the possibility of flipping an odd number of axes, then you enhance SO3 to O3. Now remember, you got to do an odd number because if you have an even number of axes and you flip them both, that's just a rotation. But if you flip an odd number of axes, you could just do 1 or you could do 3, but if you do an odd number, then you're going to get a coordinate inversion which is not affiliated with a rotation. Okay, I mean, here we go. You can't take that and rotate it into that. Okay. So parity is a possible symmetry I mean, you know, we talked about how SO3 is an important coordinate symmetry, and then its promotion in the 1 plus 3 dimensional case to SO1 comma 3. But we should always go back and ask, well, is this a symmetry? I mean, if you just flip all your axes, you know, does everything look the same? And it turns out the answer is no, okay? And now we have the ingredients to see why. So first of all, we're going to go ahead and do P x, y, z to P minus x minus y minus z. So we're going to flip all three of them. So our parity transformation is flipping all of them. And what we find is that a spinner becomes a transform spinner, which is gamma 0 times the original spinner. Okay? So gamma 0 is actually acting as the parity operator on a spinner. Clearly, the way that a parity operator acts on a vector is obvious. Okay, because it just takes every component of the vector and switches its direction. Okay? But for a spinner, you would expect it to be a little bit more complicated. And so in our case, it turns out, now I want you to notice, these are four-dimensional things, four-dimensional vectors, because everything's in 3 plus 1 dimensions, or 1 plus 3 dimensions. But the parity transformation we're doing is only transforming the 3 spatial dimensions, not t. Okay? We have to flip an odd number of the coordinates. So even though this is 4-dimensional, we're only going to flip 3. So parity is flipping the 3 spatials. The spinner transforms as gamma 0 psi, where gamma 0 is basically acting like the parity operator. And notice we did prove that gamma 0 squared is gamma 0. Which you would expect, because if you flip the, or sorry, it's the identity. I'm sorry. It's the identity. Where if you do this transformation twice, you're going to get back what you started with. Okay? Now, of course, this means that if we take psi bar psi, then it's going to become psi bar prime psi prime. And this is going to be psi prime dagger gamma 0 psi prime. No, it's not psi prime. It's just psi. And then this is going to be gamma 0 psi dagger. So I'm just going ahead and replacing psi prime with gamma 0 psi, but then I got to do this the same with this. So I'm going to do gamma 0 psi, and then I'm daggering it, times, of course, gamma 0 psi. And then, as usual, if I'm going to dagger this, since this involves transposition, I can do this as the product of the transposed objects, but in reverse order. So this is going to give me psi dagger, gamma 0 dagger, gamma 0. Oh wait, hold on, I can do something. Let me see, hang on a second. Nope, I'm confusing myself. Hang on. No, hang on, yeah, wait. Yeah, I think I got this written in my notes wrong. I think. Yeah, so this is going to be psi dagger. Gamma 0 dagger, gamma 0 psi. Yeah, my notes are wrong on this, but anyway. Okay, well, at any rate, this thing gives you the identity, so this is just going to give me psi bar psi. Okay? So basically, the psi bar psi combination is invariant under this parity transformation. Okay? However, if we insert a gamma 5 into this story, one can show that in this case, we're going to end up with minus psi bar gamma 5 psi. Okay? So it turns out that under a parity transformation, psi bar psi transforms as a scalar, but under the same transformation, psi bar gamma 5 psi transforms as what? A pseudoscalar. Exactly. Okay. Similarly, we can determine that if I have psi bar gamma mu psi, how is this going to transform? Under a parity transformation. Any guesses? What is this? The psi bar psi is just going to give me a scalar contribution, but what's this going to give me? Gamma, well, gamma mu is a matrix in spin space, but it's being sandwiched by psi bar and psi, so the spin part of this story disappears, and it's just a scalar. But what is that? It's a vector. This quantity is going to give me a vector. So what is it going to become after the parity transformation? Say it again? No, you're just doing a parity transformation. So look at what's happened here. You got this and you got this. So what is this going to become?
A parity transform vector.
Which is plus or minus?
Minus.
Minus, exactly. This is a vector. Okay. But of course, this probably immediately tells you that if I construct psi bar gamma mu gamma 5 psi, then just like in the psi bar psi story, this is going to transform as a pseudovector. That is, its sign is not going to change. Okay? Does this make sense? Yeah, good, good. Now, let me ask you a question. If I have a process and I want to know if that process is invariant under parity, what do I do? How do I figure out if that process is invariant under parity? I do a parity transformation. So I do the calculation and I get an M. And then I parity transform everything in the story, and then I calculate M again. Okay? So literally, I just write down whatever I'm going to get for M, and then I go back and I parity transform everything, and I recalculate M prime. If these are the same, then P is good. It's a good symmetry. I wouldn't say it's conserved, it's not a continuous symmetry, it's discrete, but it's a good symmetry. If you consider the process and then you consider the parity transform version of it, you get the same thing. So this tells you that the version of a process and the parity reverse version of it, they're the same in nature. Can anyone prove to me that the weak interactions violate parity? Exactly. The vertex takes this form. That is gamma mu minus gamma mu gamma 5. Now, of course, these vertices are going to be sandwiched between spinors and conjugate spinors. But when they're sandwiched between spinors and conjugate spinors in the calculation of M, how's this going to transform? Like a vector. And how's this going to transform? Like a pseudovector, or what we might call an axial vector. Now, what's the problem with that? If I do the calculation and I find that this has the value of 2 and this has the value of 3, then the answer is 1. that if I do the parity transformed version of that, the vector is going to change sign. Whoops. I'm subtracting them. Whew. I'm subtracting them. Anyway. Okay? So the important point is that even though a parity transformation might take a process and give you sort of a mirror image of it, here the probability of this process happening is larger than the probability of this process. That is a violation of parity. You'll see one process much more than you'll see the other, even though they're related strictly by a parity transformation. Okay? Now actually, the idea that the weak interactions violate parity is super simple. Because remember, the weak interactions only act on the left-handed doublets. They don't act on the right-handed doublets. You remember that part of the story? We're not going to go into it now, but in that unified electroweak interaction, you rotated the left-handed components of the doublets, and you left the right-handed components alone. The right-handed components appeared as singlets. I don't know if you remember that part of the story. Well, what does a parity transformation do in terms of left and right? It switches them. Well, if you look at the switched version of the story, it doesn't happen. So there was evidence from early on that the weak interactions are violating parity. Okay? So the weak interactions violate this discrete symmetry of a parity transformation. Turns out you can salvage that by combining parity with charge conjugation, where in addition to swapping all of the spatial directions, you also change, well, we would call this the particle into the antiparticle state. It does change electric charge, but it also changes other quantum numbers, not just electric charge. So it reverses all of the internal charges. And it turns out that if you consider CP together, then the weak interactions, I'll just say conserve, even though conserve is not good because it's still a discrete transformation. Okay? So CP is a good symmetry. Not. Turns out that even CP is violated, but to a much smaller degree. Remember, I said the Kobayashi-Maskawa matrix, the third generation of quarks, was introduced in order to get this violation. Okay? So we do have CP violation in the standard model. All right? It's from the weak interactions. And it's not that big. But there's one more point where you could ask, what about CPT? What if you take charge conjugation, parity transformation, and you reverse time? Is that a good symmetry? Turns out this is good. Okay? It turns out that CPT is unavoidably a good symmetry, and that argument you can make from quantum field theory. But there's a consequence of that. Does anybody see what it is?
Tachyons?
How?
Reversing time gives you
Yeah, it doesn't actually give you tachyons, but that's the important observation. If CP is not a good symmetry, but CPT is, it means that time reversal is also not a good symmetry. I don't want to connect it to tachyons. I don't want to go to tachyons right now. Okay, but that's the basic observation. CP is broken, so CPT being good means that T is broken. Okay, because this can't be a bad symmetry and this a good symmetry and this together be a good symmetry. They have to have broken parts which cancel each other out. Okay? All right, I gave a whole lecture. Actually, I gave 2 whole lectures on this CPT story before, but I don't want to go through that again, trust me. I'd much rather talk about strings. So I'll see you on Thursday. Talk about strings. If you came in late, remember your homework is not due until next Thursday, and I'm not having office hours tomorrow because